How's it going, guys? This is Andrew, and in this video we're going to do a tutorial on plotting the root locus and implementing a proportional controller or a P controller. So this video is for MBB 410 students at the University of Pretoria, Mechanical Engineering. Okay, so I'm going to quickly open Jupyter Notebook. We've got our notebook here. So the things you're going to want to import for this is NumPy's NP. From NumPy we want to get sine, cos and arc cos. We want controllers CT, and then matplotlib.pyplot as PLT. Then lastly, from the module added control funct we want to import nbrlock find. So an important thing to note is added control funct is a module that was programmed or created by the professors at the University of Pretoria. So if you are not a student, I don't think you can get access to this without asking for it. But it's not super important. As you'll see later, you don't really need it. It's more for really accurate values. And then nbrlock find basically stands for notebook root locus find, and it finds the k value. So getting on to plotting, first we create the transfer function, run the cell, shift enter. Okay, first we've got to run the cell. Okay, and that gives us our transfer function. Note that I've used ct.minreal, and what that does is it simplifies the equation. If there's additional or unnecessary complication, it solves it basically to its simplest form. This is important because sometimes this can affect the actual solution, so just be aware of that. Okay, basically what is the root locus? So I definitely suggest you go watch Brian Douglas videos on YouTube. He does very good videos on explaining everything about the root locus, drawing it, how different positions in the S-plane manipulates the response of a system. Go watch that set of videos, it's absolutely brilliant. Okay, so basically the poles of a transfer function are the S values for which the denominator equals 0. So it's the S value here that's going to make this denominator 0. That's a pole. And then a 0 is the S values which will make the numerator equal to 0. So now what we're going to be doing is finding a k value. We're going to multiply this by k, and for different k's you're going to have different values of s which make a pole. So the root locus is a plot of the poles of the transfer function with a varying value of k. A proportional controller is finding a specific k and multiplying g by it and then plotting that system. Okay, so plotting the root locus, I'm using the magic matplotlib qt5, and you'll see the reason why. Now plotting the root locus, we use ct.rlocus of g, which is the open loop transfer function. This is the open loop transfer function here. Note that when we plot the unit step response, it's the closed loop, which means we give this feedback. When we plot the root locus, it's the open loop transfer function. Then something else to note is you can give this a range of k values from 0 to whatever. I've used linspace here to define a range, but you can also use mp.arange. You don't have to give it a k range. Sometimes you can do things by giving it a k range, but that'll come later. This is just the basics. Then plt.grid true gives the root locus a grid, which makes it quite nice. It makes it more presentable. So now the other thing that we want to draw on the root locus, let me plot it quickly and show you what it looks like first of all. Okay, so here it is. The root locus is the blue. The x's or the pole is the pole of the system at k equals 0, and the orange is the zeros. So for k ranging from 0 to infinity, the root locus moves from the poles to the zeros. Okay, so this green line I'm going to explain to you now. What is the green line? So when we're given a % overshoot requirement for a system, for a transfer function, we can find a zeta value, which is a damping ratio, from the formula sheet, and we can get it from the graph or from the table 5.2. So table 5.2, let's say for example they give us percent overshoot of 9.5, then your zeta value is 0.6. You can interpolate this, I'm pretty sure, or you can just use the graph. The accuracies, you don't have to be super accurate with this. You can get a approximate number. So for a maximum percent overshoot, which is common in MBB of 10%, it would be what, 5.9, 5.8, whatever. Okay, so I'm going to use a zeta value of 0.6 for a percent overshoot of 9.5. Okay, to draw this zeta value, to draw this damping ratio on the root locus, that's that green line, we say x1 equals negative 100 multiplied by cos arc cos zeta. This gives us our x value, and then the y, because cos is for x and sine is for y. Then y1 is 100 sine arc cos zeta. The reason we've got a negative and a positive is because on the root locus we're always on the left of the imaginary axis, which is negative x values. So these are all negative. So you want your cos to be negative and your sine to be positive. Okay, so that's the reason for the negative and the positive. And then we say plt.plot 0 to x1, 0 to y1, and that'll give us our line. Okay, cool. So that's the formula sheet. Now, finding an S value and then finding the associated K value. So now if you notice, when we plot this, we can now come here and click on here and it'll give us a black square. Sometimes this doesn't work. You've just got to close and re-click, and sometimes it's just a mess. The idea with the zeta value is you should choose a point on the root locus which is lower than this this green line and on or above the real axis, because technically the green line should be here and lower, because this is a mirror image of each other along the over the real axis. So we're going to choose that, and that's going to be our S. Notice that it pops up here, and our gain K should be 16.89. Notice that this also comes up over here underneath the block where you're plotting. So we're going to copy this, and when we use NBR find, we should get a gain of 16.89, and it will give us a more accurate value. That's why I said you don't really need NBR find, but we use it because we want an accurate value. So let's replace our S there. That's just one that I used before, and enter, and that will give us K. And poles is going to plot another. Poles is going to plot these red X's. So that's our choice for there. Okay, so that gives us our K. Now, implementing the proportional controller, we're going to multiply our G with this K that we've just found, and that's going to give us GK. That's our compensated system. Now, to plot the unit step response of that, we give it feedback, because remember we always plot the closed loop transfer function of the system, and that's going to